Hi everyone, this is the start of our new unit of work which is called calculus, and we're going to start the unit by having a look at rates of change, specifically average rates of change versus instantaneous rates of change. So let's explore that. Let's consider perhaps we're going for a trip to Launceston, and this graph will show how as time passes we go certain distances. So this would be home, and let's just say we'll do it in blue. Let's just say that we travel for a little bit, like so, at a certain speed, getting out of home, and then we hit a highway. So we go a higher speed, like so. Then we hit a town, so the speed would drop off a little bit, so it's a lot slower rate of change of time versus distance there. And then maybe a little bit more speed, a little bit of a highway there. Then we get to Campbelltown, say here, and we stay in Campbelltown for a quick snack. So, as time progresses, there's no distance travelled at all. And then a final burst of speed to Launceston, like so. And let's just say that's about 200 kilometres away. So on my graph, I can mark that as 200 kilometres. And let's just say it took us 2.5 hours to travel that distance. Okay, so we've travelled 2.5 hours, 200 kilometres. Okay, so as you can see from this graph, based upon what we've done here, we've got different speeds that we've travelled. So here we were travelling a little bit more slowly, and then here we travelled a little bit faster because we can see that the distance increased quite significantly for a small amount of time that's passed, and then slowed down again, a bit faster again, then it stopped from here to here, from here to here, and then there's a bit of a burst of speed back to Launceston. Okay, so we had lots of different speeds there. Now, an average speed for the journey would be given by this red line. So we would just say, well, this is where I started, this is where I finished. I'm not going to get a very good line here. Maybe I'll try and use the line tool. And the average, try that again. No, that's not going to work. I'll just use the line tool. And the average speed would be given by this dashed line, right? So that would be looking at how many hours I travelled and how many kilometres I travelled, and that would give me my rate of change. So in this case, I would have, 200 kilometres per 2.5 hours. And then if I work that out by down into a per hour rate to give us our kilometres per hour, that would be 80 kilometres per hour if I just divide both sides by 2.5. So once I have got my speed here, this speed would represent an average speed, right? Because it means that from here up to here, if I travelled at 80 kilometres per hour for the whole time, it would take me 2.5 hours to get there. Okay, now average speeds are quite useful in some ways. Average speeds are useful because if you can say things like, well, if I travel some of my journey below 80 kilometres per hour, then I'm going to have to travel above 80 kilometres per hour for parts of my journey to make sure I get there in 2.5 hours. If I go above 80 kilometres per hour at some stage, it means that maybe I can afford to have a rest at some stage in Campbelltown or whatever, and I'm still going to get there in my 2.5 hours. So that's basically average speeds are useful. However, what they don't tell us is what's happening at any particular point. So if I said, well, how fast was I going on the highway? The average speed doesn't give me that. Because if this is the highway bit, then that bit needs to be worked out separately, doesn't it, really? Or if I said, how fast was I travelling from Campbelltown to Launceston? The average speed doesn't necessarily tell us. It could be a bit faster than that, could be a bit slower, I don't know. Or it could be saying, well, how fast, where was I in my journey after an hour's time? Now, the blue line will tell me that. If I go across an hour and then up to the line, I can work out how far away I was from home. But of course, the average speed wouldn't tell me that at all, because if I was following the red line. So average speeds, whilst useful, don't tell the full story. And in order to tell the full story, we would have to break our graph down into those separate parts, which we can do. I mean, the way I've graphed it here is bunches of short straight lines. So if I wanted to work out what the speed was for a particular part of the journey, assuming it was a uniform speed, then I could actually look at just part of the journey here and work out the gradient, the slope, for those particular parts, because the slope, of course, is the rate of change. An issue, I guess, is that it's probably not even that simple. It's probably, if I had to sort of draw the graph of speed as it really was, it's probably more likely to be sort of, I don't know, probably not that bad, but it's, I've probably, braking to go around corners and all that kind of stuff probably means that the speed is probably a little bit more variable than I've got there. So I guess that's what we need to do in this unit is perhaps look at how do I take a graph and work out the rate of change, that's the gradient, at any particular point, rather than looking at averages across the whole distance. So let's have a look at a different example. I'll just grab my second example here. And let's just say it's, I don't know, something like a golf ball being hit or something like that, where the ball travels from resting point here. I'll do it in blue. Resting point here, and it travels up in the air for a certain height and then lands down here. A nice parabolic curve. And let's just say that that's 100 meters away. Okay, so we can get other information from the graph to work out the function. So if we know, for example, that the height was 50 meters at its top, so that point there, then we can sort of work out what the function would be. So let's work out the function. Well, let's not work it out. I'll just give you the function. So we could say that the function of the graph is 2x minus, and I'll use decimals here because it just makes it easier to conceptualize, minus 0.02x. Okay, so that's the function that would give us this nice parabolic curve with a top height of 50 meters before it falls back down to the earth. I know that this curve is probably a little bit too sharp on the down here, but you get the idea. Okay, so if I were to use averages, again, I'll just use red for that, then I can talk about the average, so this graph, I should say, graphs distance, horizontal distance versus height. Okay, so this here, for example, was the top height of the graph. Everywhere along this blue curve tells us how high the ball was traveling for a particular distance. So the rate of change is how much distance is being traveled per height that has increased. And because it's a parabolic curve, we can see that it starts off slower but gets a little bit faster up to a particular height, and then it drops down again as well. So the rate of change of distance to height is changing all the way along the graph. Now, if we used an average, that would give us some understanding of the height per, the distance per height, or height per distance across, but it doesn't really tell us a very good story. In that, if this is the line that would be given by that, if I was trying to work out, well, how quickly was the ball climbing into the air at, say, this point, it doesn't really tell us. If I use the average rate, it would actually be giving me a much more slower rate than it actually was. So what we need to do is we need to be able to get something a little bit more accurate than using this giant average here. So I'm going to stop the video for a second and get you to maybe think about how you could get a more accurate picture of what's happening at a particular point on the graph line than using this big average over here. What could you do? Okay, so hopefully you've had a moment to think about that and maybe work out what you could possibly do. Let's just say this is the point we're looking for. I'll do it in red as well so we can sort of see it. And you're trying to work out what this, how high the ball was climbing at that point. Well, one thing we could do would be to work out the gradient just a little bit further away. So maybe pick a point either side here and draw the gradient straight line there. That's still an average, but if I just zoom up, I hope this zoom up works. But that average has to be better. This average here has to be better, doesn't it? Because I'm picking 2 points really close to this point. And so it's getting closer to what the blue line is. And in fact, why don't I just choose the point itself and another point close by? So what about this point and this point here? Like so. So there's the rise. Sorry, I'll just do the pointer. There's the rise. There's the run. So we can work out the gradient, and the gradient is pretty close to that blue line. Even better. Oops, forgot my zoom tool. Even better. How about I zoom up even closer and choose a point? There's my rise and run there, and I can now look at the rise and run of this tiny distance. That's going to be even closer to the blue line, isn't it? So the closer I bring this dot, this point, to this point here, the better it's going to be in terms of getting closer and closer to that blue line. So what we want to do, and this is the heart of differential calculus, we call it. At the heart of it, what we're doing is we're trying to find a dot 2 points so close to each other, the point we're interested in, this giant dot here now, and a point right next to it, so that the gradient is basically the same as that point. And we can say that this is the instantaneous rate. It's the rate at that point. So we choose a point really, really, really close. Now, the method by which we do that is quite, well, it feels like it's going to feel like it's a trick, but it's not. It's not a trick. It's not tricksy, really. Okay. So, sorry about these things popping up. Oops. So, there's our graph, like so. And what we're going to do now is we're going to have a look at what the rise and the run looks like. Now we know that rise is basically, well, we know the gradient formula. Let's start off with that. The gradient formula is y2 minus y1 over x2 minus x1. Okay. Now what we're going to do is we're going to choose a point in our function. Okay. So let's make, on our function, let's say that this point here, the point we're actually interested in, is going to be the point x, some value for x, and then whatever the corresponding y value is, which is f of x. And then we're going to choose the point, you can't even see it now, it's so small, but that small point there is just a little bit further along. So let's call that x plus h being a short distance away from x, and then we're going to make the corresponding y-coordinate f of x plus h. Okay, so this is h, a tiny distance away from it. Okay, then what would our gradient formula look like with those values? Well, the gradient formula would be y2 f of x plus h minus y f of x all over x2, which was x plus h, minus x. Okay, next page. Look at, well, not next page, let's have a look at this. X plus h minus x. The x minus x is going to cancel each other out. So now we're left with, go to blue now, that the gradient is going to be f of x plus h minus f of x all over h. Now what we want to do, now h can be any value at all, but we want h to be a really tiny value. So what we're going to do is we're going to see what happens to this gradient when we let h approach 0, and this is called limit theory. And so we say that the instantaneous gradient is found by looking at what happens when h approaches 0. What happens when h approaches 0 of f of x plus h minus f of x, that's the rise, over the run. Now, this sort of terminology here, this lim is short for limit, and the h arrow 0 says h is approaching 0. Okay, h is approaching 0. So what we're really saying is that as h approaches 0, what is this value changing? Now, we're not setting h equal to 0. I wonder why. Okay, we're not setting h equal to 0. We're just letting h approach 0. If we set h equal to 0, our gradient wouldn't work at all. So we're just letting h approach 0, and we're looking at what's happening to the gradient as h gets teeny tiny. Okay, so in the next video, I'm going to take this concept and I'm going to apply it to the problem you just saw. We can see how we can work out what the gradient would be for a particular point, or any point really on that curve. So that's coming up next.